Good morning, sir. This is our third review of the project named Design of Cotton Picker and Effector. So the proposed methodology is this provides a structured approach to the design, development and evaluation of robotic cotton harvester. It actually outlines the mechanical principles, component selection and a systematic process. This actually focuses on the creating a robust and efficient system that addresses the challenges of cotton harvesting, such as labor shortages, inefficiencies in traditional methods, and the need for adaptable and cost effective solutions. System architecture is nothing but the overall structure, the structural layout and integration of the key mechanical components in the robotic cotton harvesting. It actually serves as a blueprint for understanding how the various subsystems interact to achieve desired functionality. So the components of the system architecture are end effector, robotic arm, stepper motors and drivers, power supply, support frame and cotton transfer mechanism. So we are moving towards the mathematical modeling and approach. The mathematical modeling focuses on the calculations and formulas used to design the optimized and mechanical components of the robotic cotton harvesting system are actually modeled with the help of MATLAB. And one critical aspect is determining the center distance between two pulleys using the formula for the length of an open belt. So in this process we are using an open belt for the full assembly of the cotton picker and effector, and this needs to be calculated with the help of mathematics, and length is calculated, so the length comes out to be 82.77 mm. The approach details the step-by-step process followed to design, prototype and test the robotic cotton harvester. This includes CAD modeling, prototype fabrication and iterative testing to refine the system. Then comes the part of design and CAD modeling. The design phase began with creating a detailed CAD model of the robotic cotton harvester. The CAD model includes multi-finger end effectors, then support frame for the housing of the robotic arm and other components, and third one is pulley and the belts designed for optimal motion transmission. The CAD model was essential for visualizing the system and analyzing the mechanical layout, and also to ensure the compatibility between the components. So this is our CAD model. This is a prototype 1, which was the previous design we have presented in the review 2. So this is the CAD model timeline. Here hole is generated. This is the prototype 2. 3D printing the prototype. After finalizing the CAD model, the first thing was to 3D print the prototype. The end effector and other critical components were 3D printed using the durable materials. The prototype allowed for hands-on evaluation of the design, including testing the movement of the fingers and the efficiency of the timing belt and overall structural integrity. So this is the first prototype we have 3D printed. This is the second prototype, which is shown as new, is the second prototype. The side by side comparison is shown in this figure. First prototype was in the larger dimensions, whether the second prototype is of smaller dimensions and with different design. Operational readiness. The mechanical components of the finger mechanism are fully assembled and aligned. The prototype is ready for initial testing to evaluate its cotton picking performance. Here we can see in this diagram the finger mechanism and the belt is assembled fully with the help of a pulley. This is the top view. This is the top view of the assembly or 3D printed assembly. This is the isometric view. So the changes number 2 is the closed belt. First we were using the open belt, which are very difficult to modify into closed belts due to challenges in achieving reliable and durable joints. Design updated to use industry made closed belts, because while performing different iterative tests, the open belt was actually making a problem. So eliminate that issue, we adopted the closed belt to ensure seamless operation and enhance reliability, to remove the necessity for a belt tensioner and simplify the design. So the center distance is calculated for closed belt with the help of calculation, mathematical modeling. The center distance for the open belt drive is approximately 82.77 mm, as I told earlier. So then we move towards testing and iterative refinements. Initial lab tests were conducted using 3D printed prototype. Then based on the test results, the design was refined to improve picking efficiency and to reduce cotton loss and enhance the durability of the components. The development of this prototype lays the foundation for further testing and optimization, focusing on efficiency, durability and adaptability in real world conditions. So methodology actually So the system implementation focuses on the development and iterative refinement of the finger mechanism. Goal is to create an efficient and reliable end effector which is capable of picking cotton from the balls. Iterative improvements have been made based on the initial observation during the assembly and operations. Then mechanical implementation like 3D printing and iterative tests which are performed. So the fabrication of finger mechanism, the multi-finger end effector was designed using CAD software. A timing belt. The belt is shown in this figure. A timing belt mechanism was integrated to drive the rotating pins for efficient cotton picking. Then the full assembly. The fabricated components including the timing pins, supporting structure were assembled into a functional finger mechanism. Iterative refinements. Okay, so the results are improvement in picking efficiency, the design of the finger mechanism has improved in terms of reliability and ease of use. The current design allows for better handling and movement, but the actual cotton picking performance will need to be tested in the field conditions to determine the system's picking efficiency. And the challenges with the first prototype were the first prototype had larger dimensions and used an open belt, which caused operational issues like the belt was difficult to close and it was frequently getting stuck in the timing pulley. But these challenges were addressed in the second prototype. This was our first prototype and this is the small is our second prototype. So all the issues were addressed in the second prototype by reducing the dimensions and using an industry made closed belt. So this black is a industry made closed belt which significantly improved the functionality and reliability of the system. So So the design refinements, like while the second prototype is an improvement over the first, further refinements are also necessary to optimize the system. And then the further testing. So testing is seen to be critical in determining the overall performance of the system. Further testings will also help identify any mechanical or design flaws that need to be addressed before the system can be used for larger scale cotton harvesting. And the potential for the commercial use. The system holds potential for commercial use and can be adopted over the manual mechanical way of cotton picking. These are some results which we were doing experiments on this. So here we can see the lab test and field test are shown. So the average picking ratio and picking time per ball is shown. So because of the different changes and improvement we have done in the design, we have got the fastest picking ratio, and as 2.4 second, 1.5 second, like this. These are in the seconds per ball. And the conclusion is like we identify the opportunities and improvement and innovation in the field, addressed existing challenges by integrating advanced technologies such as servo motors, stepper motors, and color sensing cameras, and by adding and integrating the close belt. So the development has made significant progress, particularly with the successful design and fabrication of the finger mechanism. This mechanism, featuring a multi-finger end effector with rotating pins and a closed belt drive, has shown promising improvements over the previous prototypes. So in conclusion, I would like to say the shift from an open belt to closed belt drive has resolved operational issues such as belt misalignment and getting stuck in the timing pulley, making the system more reliable. Thank you so much.